Hello ladies and gentlemen, and welcome to our video today on energy. We want to talk about three key things today. What is energy? What affects an object's kinetic energy? And what is the work energy theorem? So let's get started. Now, in your reading that was assigned to you in class, you read about kinetic energy and the work energy theorem. So we're going to talk about those ideas very briefly because you have some experience with them already. We just want to cover a few key highlights with that. So we really need to talk about what is energy, because I don't think the book does a good job explaining what that is. So let's start off with that. What exactly is energy? We can think of energy drinks and, those little 5-hour energy capsules and things like that as, okay, what's that actually do? That's more chemistry than physics, so we'll pass that off to another class. But we will actually come up with a definition for what energy is. And that definition is going to be as follows. Energy is basically the ability to do work. And what that means is, if something has energy in it, it can do work on other things. Take, for instance, a baseball. If you throw a baseball at an object, when they collide, the baseball is going to push the object and have that move, or it could be the ball bounces back, one of the two. But in either case, the ball has energy, and when it hits something, it can transfer that energy to something else and cause work to happen. And that's going to be one of our key ideas in this section. So we're going to consider energy as the ability to do work. Now, what types of energy are there? Well, there are all sorts of types of energy we can talk about. There's some up here on the screen we can just consider very briefly. We have thermal energy, which is the internal energy of an object's molecules. Now, in terms of heat, when you heat something up, that makes the molecules inside the substance move faster and faster. So hot objects, for instance, have very rapid molecule movement, whereas colder objects have much slower movement. So that's one way we can look at energy. And thermal energy is very prevalent throughout the entire universe. There's laws written about it. We're not getting into that right now. Second type of energy we can talk about is chemical energy, and that's the energy stored in a substance due to how the particles are arranged. That can be atomic bonds, that can be an internal structure of electrons, all sorts of things like that. In that case, we're actually saying that the substance itself has an energy that can be transformed by doing something with it, by breaking those bonds or some other action. Taking that a step further, we have nuclear energy, which is the energy due to an element's composition and how it changes. For instance, radioactive decay, that whole idea is that that element is actually shooting off electrons or neutrons, and that's actually changing what the element is. So that's a type of energy. But the type of energy we're going to concentrate on for this chapter is mechanical energy. And that is energy due to motion or due to forces acting on something. And there's actually two key types of mechanical energy we're going to talk about, which are kinetic energy and potential energy. Now, potential energy we're going to get to in another video. In this one, we're going to focus on kinetic energy. So let's identify that. Now, this was in the reading. We say kinetic energy is the energy in a moving object. If you have an object that is moving, it has kinetic energy. It doesn't matter if it's a large object, a small object. If there's motion, there's kinetic energy. And it depends on the speed, first of all. For it to be moving, it has to have a speed to it. And it also depends on the mass. And the way they're related, as you can see in the equation there in the center, is the kinetic energy is 1/2 times the mass times the speed squared, or we can call it Ke equals 1/2 mv squared. So what this shows us is there's a direct relationship between the mass and the kinetic energy. The more mass you have, the more kinetic energy you're going to have. Also, it's proportional to the speed, but it has to be the speed squared. And this is a key thing here, because that tells us that any change in speed is going to have a dramatic effect on the kinetic energy change. This is why we can have projectiles that are very small and light, but moving extremely fast. They can do a lot of damage. It's because that speed term, since it's squared, that can have a huge effect on the kinetic energy. So that's something to keep in mind. Now, in terms of some of the background stuff with this, it is a scalar quantity. We are not concerned about direction of kinetic energy. So again, it's just going to be like work. It's going to be plus or minus. And also like work, and it turns out this is true for all types of energy, the units we're going to be working with are in joules. So let's take this idea and apply it to a situation. Let's say we have a tractor-trailer truck moving at 75 miles per hour and a car moving at 75 miles per hour. We want to know which one has more kinetic energy. So take a moment to think about it. If you want to pause and think about it, that's fine. And what we can find is, well, they both have the same speed, so the v squared term is going to be the same for both, but the masses are completely different. You should be able to identify that a tractor-trailer truck has more mass than a car. So since the truck has more mass, that means that the tractor-trailer truck is going to have more kinetic energy. So how can the car have more kinetic energy than the truck? Well, if the car were to speed up, that can increase that speed term, which since it's squared, it should be easier to catch up, so to speak, with that. So that would be the way we could do it. We could speed up the car, and that would be able to move their kinetic energies closer to each other. Now, the last idea we need to talk about with this is, how does kinetic energy relate to work? And there is a relationship we need to consider, and it is that if work is done on an object, it gains kinetic energy. If something has kinetic energy, it can do work. You can see those two ideas there. If you have kinetic energy, it can do work on other objects. That goes back to our baseball example from earlier. You have a baseball, it hits something, it can do work on that. In a similar way, if you do net work on an object, it's going to change its velocity. So that can be, for instance, if you do net work on a box, if you push it and you're overcoming friction, and there's a net force causing an acceleration, you're going to change its kinetic energy. So we can relate work and kinetic energy in the following way. The net work done is equal to the change in kinetic energy. So you can see that equation down there. That is an equation we're going to be using in class. And you can write it as W net equals delta KE, or if you want to break it down a bit further, that the net work is equal to the final kinetic energy minus the initial kinetic energy. We will be using all of these ideas in class to solve problems. We're going to start off very briefly with just using the kinetic energy equation and then work our way up to using this work kinetic energy theorem. But the goal of this chapter is we're going to learn about later on potential energy, and then we're going to relate them all together into how we can analyze the motion of an object in terms of its energy at the start and at the end. So, if we go back to the questions we asked at the beginning, we said, what is energy? We talked about that energy is just the ability to do work. We asked, what affects an object's kinetic energy? That was mass and speed, mainly speed, since speed is squared, that's going to have the more direct impact on it, so to speak. And then what is the work energy theorem? Just the idea that the work done on an object is going to equal its change in kinetic energy. So, that is it for this video. The next one you'll be watching will be on potential energy, and I will see you then, so to speak.